That we looked at yesterday is we talked about the fact that when we look at a chemical or physical process, that chemical or physical process is either going to be a spontaneous process. We said that once again in the video yesterday, that if it's spontaneous, then we consider this thing to be thermodynamically favorable. We said that we had non-spontaneous. And remember, when it comes to spontaneous, it simply means that it's going to occur without any outside intervention. Non-spontaneous in this case, we said that this thing is non-thermodynamically favorable. If I want to make it do something, such as make, in this case, this Sharpie go to a higher height, I gotta put energy into it. That is non-spontaneous, non-thermodynamically favorable. And if I let it go, hey, that's spontaneous, thermodynamically favorable. And then we said we had these things such as equilibrium, where equilibrium simply says it goes back and forth in the exact same path, and no net change to the universe entropy. And we'll talk about entropy today. Examples we saw, hey, spontaneously going down here, thermodynamically favorable. We said, hey, non-spontaneous, he's not going back up that hill. If anything, once again, non-thermodynamically favorable. We said that in this case, if we didn't have friction, then we got something that's going to be our third condition, which is going to be our equilibrium in this case. Things that we said yesterday also is we said that things that happen to be spontaneous in one direction, such as this water falling down, is going to be non-spontaneous in the other direction. Whether it's a physical or chemical process is going to play out. We talked about the nail. Hey, nail is shiny. It will spontaneously rust, but it's not going to spontaneously go back in the other direction in this case. And that's all I'm going to say. Let's skip over all the rest of it because once again, you can watch the video to kind of go over it. We talked about how temperature affects spontaneity in this case. And we're going right here to this reversible process. And if we look at it, we had several different types of reversible processes. And remember, one of the things that it says these reversible processes are at some constant temperature. So long as I have it at a constant temperature, then hey, it's going to be at this equilibrium. Just like I know water will freeze and also melt so long as I keep the temperature exactly at 0. But if I play around with this thing, first of all, if I want ice to melt, do I have to put heat on this side or on this side here? I want the ice to melt. Thank you, on this side here, wouldn't I? Well, if you think about it from Le Chatelier's principle, at 0 degrees Celsius, it's going back and forth, back and forth, back and forth. If I put energy into it, it's gonna, once again, Le Chatelier says, hey, that energy that you're putting in, it needs to now push this thing in the forward direction to kind of get rid of it, and you're seeing the melting process take place. So long as we keep temperature constant, I got good equilibriums. Same thing right here for this chemical equilibrium. It's perfectly fine. But if I change the temperature, it's either going to favor the forward or the reverse, depending upon whether it's endothermic or exothermic here. All right, continuing on here. So if you look at it, I can tell with this process right here that once again, it is going to be at equilibrium. However, if the temperature was above or below 0 degrees Celsius, the process would not be an equilibrium process. But instead, I'm going to say this process is going to be spontaneous, non-spontaneous, or is it going to be reversible? Which one would it be? If I raise the temperature above 0, or I lower it, spontaneous, non-spontaneous? Wait, which one is it going to be?
Spontaneous.
All right, let's go with this route. If I increase the temperature above, in this case, 0 degrees Celsius, is this thing just like, hey, I'm still equilibrium? Or is it going to just start proceeding in one direction? I don't have to do anything in this case. It's going to be spontaneous. In this case, if I was to have a high temperature, so you know what? Temperature greater than 0 degrees Celsius. Then I know what's going to happen. It's going to spontaneously, I don't have to do anything. It's just going to start melting. It's not going to go back and forth in this case. At the same time, if I take the temperature and I make it lower, so I go to temperature less than 0, then it's going to say, you know what, I'm not here anymore. I'm going this way, and I'm going to continue going that way so long as you keep that temperature below 0. Yes?
How does like adding heat or like temperature like not count as acting upon it? Like wouldn't that be?
Well, I'm just saying that equilibrium is only good at that given temperature. Just like how we saw, remember when we looked at equilibriums, we always said that equilibrium constant right there is only good at that temperature. You change that temperature, that equilibrium constant is going to change because it's either going to produce more of the products or it's going to produce more of the reactants. So I'm just saying that if I went with some new temperature, then that's not at equilibrium. And that's all we're saying. We're just going to say it's not going to be spontaneous anymore. Matter of fact, give you a good example right here. If we look at this example right here, we got ammonia. I'm saying, hey, at 25 degrees Celsius, at room temperature, I got something that looks like this right here. And what we need to look at is, hey, is this thing endothermic or is it exothermic? And clearly, I'm going to put the delta on the reactants or product side based upon what I have up here. So it goes on this side over here. Products, so it goes over here. Which side does it go on? Thank you. Hey, my Irish chem students had a test over that. They know that if it's negative, that's release. That's exothermic in this case. So if I look at 25 degrees Celsius, this thing is going back and forth, back and forth. It's a reversible process. However, if the temperature was increased, this thing is not going to be at equilibrium anymore. If I increase the temperature, then this thing is going to proceed in which direction? The reverse. Remember we said always treat temperature when it comes to Le Chatelier's principle like it's a reactants or product. I know if I put more ammonia on here, it's going that way. If I put more heat into this thing, then it's going to consume the energy that I put into it, store it in the bonds, it's going to start producing this thing right here. And it's going to continue to proceed that way until it reaches its new equilibrium. So we can take something that is reversible and make it spontaneous by playing around with the temperature here. Now, when it comes to spontaneity, making things spontaneous, there are two driving forces that we have. And driving forces are simply these forces that are going to push this thing to be spontaneous. And the two driving forces that we're going to take a look at is energy and entropy. This is what Mother Nature likes. It likes to use these two things to determine whether or not something will be spontaneous in one direction. Of course, spontaneous in that direction is not spontaneous in the other. Or it could possibly tell us, under these conditions, you're going to be reversible in this case. Now, one thing that I know already is that Mother Nature likes low or high energy. Low. So that's going to be one of the great driving forces. We're going to see, hey, when we can go to low energy, that's going to be a good thing. So here we go. If I got a ball up here, I know the ball is going to roll down the hill. I don't do anything to it. Same thing. It's going to try to get over to the product side to get the lowest possible potential energy. So when we look at the majority of reactions, a lot of reactions are going to end up being spontaneous because they happen to be exothermic. That's what we want in this case. Keep in mind that we can use the standard heat of formation to kind of figure out what in the world is going on with the actual change in energy. And remember, even when it comes to the change in energy, we're calculating in a sense like this right here we said is our delta H. What does delta mean? Just, I don't care, delta for any delta V, delta T. It means change. And it's always final minus initial, initial minus final. Final minus. That's why we always say, you're the final thing, right? You're the initial, and that's why when we look at the actual calculation that we've learned, we've always said that, hey, it's the moles times the delta H of formation of products. And we do that for each one of the products, and then minus, and we do the exact same thing for the reactants. So I know you could do a problem like this one. I'm going to show you the actual solution. The reason why I know is that 98% of the students on my last test for honors aced this thing. They love this equation. Because all you do is go in and simply say, hey, I got 4 moles of U times, and once again, these values are given to you. Take care of that part. Then minus, and I do the exact same thing for the actual reactants. 1 mole times its standard heat of formation. Plus, since it's sigma, I got to do the same thing for the next one, and times it. And then once again, when it comes to this problem, bring it all together and it says, hey, this thing is giving the universe exactly what it wants. It is exothermic in this case. Perfect. One last thing. I just want to point this out because I gave this on the AP, not AP, but the honors chem test. Let's see if you remember it. because you might be asked, and I actually asked you this on the test. I said, hey, you know what? This is actually the standard heat of formation of water. Write the thermochemical equation. Now, I made it as a multiple choice for the actual honors chem students. And they had to choose which one was going to actually be the thermochemical equation that would represent the standard heat of formation. And the only way you're going to remember this, or give me the right answer, is to know standard heat of formation. If you remember, does anybody remember what it's going to be? Like, what is standard heat? It's defined as producing how many moles of water? One. From its what? I do agree. So it's going to be, literally, I got 4 assists to just be 1 mole of water produced from its elements. Just the only reason I'm pointing that out is just in case AP says, hey, you know what, which of the following would represent? Now keep in mind, this is not right yet. I still gotta go in here and make sure this thing is balanced. And to make sure it's balanced, I would have to do something like this right here. That is, once again, that value would go along with this reaction right here. Just point it out. But for us, once again, we're going to go through and just use this to be able to calculate what the standard heat, not standard heat, but what the delta H of the reaction is going to be. Easy enough. Now, one of the problems that we run into is what if we have something that looks like this right here? What if we have an endothermic reaction? And if you look at endothermic reactions, Mother Nature is like, no! What in the world are you doing here? I'm not happy. I'm happy going downhill. I will not spontaneously go up this hill. And for a long time, scientists were perplexed. Like, I don't understand. I know this thing curves. I know for a fact that if I take this and I place it in water, it will dissociate because, hey, that's ammonium, that's nitrate. It's completely soluble. If you remember, there's 2 things that are driving forces. There's enthalpy and there's entropy. And for those of you, some of you might know, entropy is, and I've said it in honors, and I might have said it in this class in AP maybe once or so. We said entropy is just a measurement of what?
The increase in complexity in the universe.
Exactly, the increase in the complexity of the universe. Or we could just simply say it leads to more what? Chaos and disorder. But I love your definition. That was very formal in this case. But if you look at it, it's more chaos and disorder. Watch what's going to happen here. I got this ionic compound. And remember, ionic compounds like the alternating cations and anions, and this is kind of how the crystal looks in this case. Is that a high degree of order right now? Now, if I was to take this, and if I dissolved it in water, then I really need to take this whole thing and really do what with it? Flip it over and dump it out and let these things start mixing. Can't you agree that's a lot of chaos and disorder? That's really the driving force of this endothermic process. It's the fact that it has to have so much chaos in this case and disorder. And one of the things that you could see is AP could give you something like this. And they could say, hey, we got this endothermic process that's occurring spontaneously. Then what could possibly allow this thing to occur? And it's always just going to be the fact that clearly it's just going to have more disorder. Because what I guarantee you is if you have a whole bunch of order and you have things going up the hill, I'm here to tell you, I 100% will tell you that it will not be spontaneous. I just can't ever get it to go. It's not gonna happen. I gotta have one or the other. I'm gonna show you eventually an equation that we can use that will allow us to actually calculate. Like literally, we'll plug numbers in for this thing. It'll kick out an answer and say, oh, that's spontaneous. We'll plug in numbers, and if you look at it, you're supposed to see it in AP biology. Years ago, I used to always show this, and people in AP biology like, oh, well, they wouldn't know the equation, but they would know this right here. Have you learned delta G? Called Gibbs free energy. Man, it's unfortunate. But that's okay. You're going to learn in my class in this case. But if you look at this thing right here, delta G Gibbs free energy, which we'll talk about tomorrow, it governs the universe. Before I even mix 2 things together, I can plug numbers in here. And I can say, you know what? This reaction is about to be spontaneous. No, the reaction is non-spontaneous. Uh-oh, nope, the reaction is going to be at a reversible process as an equilibrium. It's like, to me, like an equation that tells us what is going to take place within the universe. And if you look at the equation, what is it made up of? Those driving forces here. And also, one of the things that we said that could change something from being spontaneous is temperature. It even drops temperature in there in this case. So we'll take a look at this equation tomorrow. But what we need to talk about is we need to talk about entropy. And this process right here kind of illustrates, before I get to entropy, the same thing we just saw. This is looking at a physical process. And if you think about it, ice will spontaneously, look, here goes H2O as a solid. It's no equilibrium. It will go H2O as a liquid. Remember we said, things that are spontaneous, we don't use the equilibrium, we use the arrow here. So long as that temperature is greater than 0 degrees Celsius, it's going to occur. But if you look at it, we said that this was an endothermic reaction. Doesn't make sense, because once again, it goes against the universe. That's higher in energy. But if you think about it, ice in the solid state, very organized. In the liquid state, they're slipping and sliding, they're all over the place. And if you don't believe me, take a block of ice. It's easy for me to take that block of ice and hold it right here in my hand. But if you took that same block of ice and you put it as water in my hand, it's all over the place. It's going to be a mess. So what we can see is that the reason why this thing will technically occur so spontaneously is because entropy is going to be the driving force for this thing, getting more chaos and disorder. And this is kind of showing the water in the solid state versus more chaos and tumbling around those water molecules where they're not in a fixed location in the liquid state. Now, in this picture right here, this is Mr. Griggs' dorm room. And if you look at his dorm room, and I remember visiting, I took a picture of his dorm room. I was like, oh, gosh, Lee. And I said, gosh, Lee, your dorm has a lot of entropy right here. And Mr. Griggs was like, hey, you know what? I'm just doing what Mother Nature wants me to do in this case. And what I want you to tell your parents, but don't tell them I said this, because I had nothing to do with this. But the next time they tell you that, hey, your bedroom is a mess, clean it up. Say, I'm just doing what the universe wants. I'm allowing it to be happy in this case. Because if we think about the universe as a whole, it naturally goes to chaos and disorder. It is hard for you to keep all your notes organized in a binder, which a lot of you don't use anymore because you have notability. But back in the day, when they didn't have notability, oh my gosh, I used to look at students' binders and papers were flying all over the place. My desk up here, once again, I'm not gonna fight it. I had cleaned this desk up, and I remember like a day or two later, it was right back to the chaos and disorder. That's what the universe wants. Also, if you think about it, if we go back a long time ago, back when Mr. Chopin was a little itty bitty lad. I can't say that. Would be terrible to say.
Say it.
No, I can't. Say it. No, because it would be awful. And you can go tell Mr. Chopin. All right, so when he was back when he was a little lad.
No, we won't.
Here we go. When he was a little lad. Here we go. We're keeping on going. When he was a little lad, there was this thing known as the Big Bang. And he was around. He got a chance to actually watch it. And when the Big Bang took place, basically what ended up happening is all the matter, of course, was got combined right there in a little small object, in this case, maybe the size of basketball. All that mass right there. If you think about it, the universe was really organized. If you wanted to find anything in the universe, where is it? It's right there. But then, boom, it starts to spread out. Starts to be more space. And as it occupies more space, that's more chaos and disorder. The analogy I always give is, hey, if we're at a dance, and the dance is really crowded, we could be like maybe a solid. What do solids get to do? They get to vibrate, right? And they'll be like this, like, hey, that's all I can do. I can vibrate. That's it. I don't have much motion. I can't even move my arms. It's so crowded at this dance. But as things start to spread out, I get a little bit more room, I can start, hey, look, I get to move my arms a little bit. I can do the wave. I can do all, hey, I can slip and slide. And as there's more and more room, I can start doing the moonwalk. I do whatever I want. As we get more room, there's more room for chaos and disorder that can play out here. So when we look at entropy, entropy, once again, is just measuring how much chaos and disorder do we have. And keep in mind, the larger the value, the more chaos and more disorder we have. And what we'll be able to do is somebody has a large value versus somebody has a small value, I can say, you got more chaos. you got less chaos down here. So it's just looking at what the magnitude in this case is going to be. And once again, I tell you, hey, drop a stack of papers, it's going to go all over the place. It's not going to stay organized. So here we go. We've got some values that are up here, where it's given us, in this case, the actual entropy. And if you look at the entropy, it's going to be given in joules per Kelvin moles is the unit that kind of goes along with it. But I can start seeing that different things have different degrees of entropy. Even I look at it. Wait a second. Hold on. Who's going to have, without looking at your notes, more chaos and disorder? The liquid water or the water vapor? Water vapor, exactly. Just like you see right here. You're going to be less, you're going to be more, and you're going to even be more in this case. And you'll notice that when you look at the actual values, that's what we're starting to see. We can easily see the chaos and disorder by simply going from one state to another in this case. So we'll have these tables. Now what's cool about these tables is you'll have the opportunity to calculate the change in entropy for a chemical reaction. And when it comes to calculating the change in entropy for a chemical reaction, they'll give you these values. And then you got to do this new calculation that you have never, ever, ever, ever seen before. And it looks like this right here. Delta S is equal to sigma n delta S products minus sigma n delta S. It's the exact same reaction we use, or equation we use, for delta H. And whether you realize it or not, the delta H is on the equation sheet, and right underneath of it, this equation is on the equation sheet as well. You're not changing anything. The only difference between this and a delta H is I just gotta put the delta S in here in this case. So easy calculation if you look at it. I didn't want to insult your intelligence, so I went in here and I did it for you in this case. Where I went in and said, hey, they gave me the values, and for that exact same reaction we just looked at, we calculated the delta H. We'll see that, hey, if I substitute in and plug in instead of the delta H is the delta S, products minus the reactants, I get something that happens to be negative 15.6. That's not really that great, to be truthful. Because if anything, it implies that things are getting pretty organized here. So we'll talk about this in a second. So we'll come back and I'll explain what's going to happen here. So if we look at driving forces once again, energy and entropy, and those two values are delta H and delta S, eventually we're going to throw it in a Gibbs-free energy, or Gibbs-free equation, the equation I kind of showed you. And we're going to kind of figure out what's going to happen. Because one thing in the universe is like, hey, this is great. It was exothermic, delta H was. The other thing in the universe says, hey, I'm going towards more order in this case, because it was like negative. It's becoming highly organized. So here we go, a couple of things to point out. Things the universe wants to see, low energy. Which means that if it's going to be low energy, then we're looking for delta H of the system, or we can say delta H of the reaction as being negative. We want exothermic, going from high energy down to low energy. How do we want the delta S to sit? We want it to sit as being positive. And what I can tell you for a fact is if you give the universe both of these, I'm done. That process, whether it's physical or whether it's chemical, will absolutely be spontaneous. Now, this table here, I'm going to have to explain to you. If you look at it, what it simply says is that if we have what the universe wants, look at right here, negative, change in enthalpy, going lower energy. Oh, that's fantastic. Hey, the entropy is positive. That means it's a lot of chaos and disorder. What I tell you right here is that it will always, always be spontaneous. But if you look at this next scenario I have right here, positive, that means it's growing in energy. You know, I don't like that. Negative, it's becoming less chaotic. It's becoming more organized in this case. You're not giving the universe anything it wants in this case, which means that, hey, it is going to end up being non-spontaneous. Wait a second. Let's have a reaction that's A plus B. Delta H here is negative. Delta S here is positive. Universe is like, hey, this is great. I love it. I'm taking place on spontaneous. But if I look at it, that's spontaneous in that direction. But guess what it's going to be in the other direction? How do I know this? Because remember that thing called, it's somebody's law that said you flip things around. What was that? Flipping equations around and put the puzzle pieces together. Hess's law. If we look at this from a Hess's law perspective, if I flip this thing around, then what happens to the delta H? It becomes just positive. What happens to the delta S? Where it was becoming more chaotic, obviously the other way, it has to be going in this case to more, in this case, order. So what I can see is that once again, things that are spontaneous in one direction, absolutely non-spontaneous in the other. Now, what we're gonna have to address is this here. What if I give the universe, in this case, something that it does not want? So right here, matter of fact, we'll do this here. Here, clearly I can see it's like, no, I'm going higher in energy. I don't like that. Here, it's like, hey, more chaos, more disorder. If we have both of these being positive, the rule of thumb is temperature needs to be high. Positive, temperature high. Now I'm going to show you why that's the case tomorrow. And you will understand it because you're going to plug some numbers into an equation. And you're going to see that the only way this is going to play out is to have high temperature. But at the same time, if you just remember plus, high temperature. Negative, well, let me see. You're happy here. I'm happy. I am sad. Negative, low temperature. Kind of goes along with it. But at the same time, I don't want you to commit this to memory. I want you to understand it, why this has to be the actual case. Now, what we're going to talk about really quickly, and we got about 6 minutes. But in the 6 minutes, it's going to be really easy. So stay with me, because this is going to, when I say easy, this is easy. What we're going to look at how to figure out whether something is leading or is going to more chaos and disorder, or is it becoming more organized? And if you look at the first part right here, I've got the states of matter. I got solid, liquid, gas, plasma. They're not going to ask you anything about, but plasma is when you literally break the atom apart into its protons, electrons, and neutrons, and it's just like all flying about in this case. I can clearly see you're organized. You're a little bit more chaos because you get to slip and slide. You're a gas. You're like all over the place in this case. And if I can break the atom into even smaller pieces, that's even more chaotic. AP's never asked you about plasma. So if we look at entropy, what you'll notice is that the entropy, and I'm using S once again as entropy, gas is highest, liquid, and solid. You already knew that. And the reason why I knew that you kind of understood that is when we looked at this table right here. You told me exactly what was going to go on with this liquid versus that gas, that solid versus the liquid versus the gas. Clearly, the state is going to change the degree of chaos and disorder that we have here. There we go. Keep in mind that when we have something that is going to be aqueous, so typically it's solid, liquid, aqueous, and the reason why aqueous is a little bit more chaotic and disordered is I know that water by itself has a disorder. The particles are moving about in this case. But at the same time, if I said, hey, where are all the water molecules? Right there. But at the same time, I close my eyes over here, I'm going to be pointing to different things because there's more particles inside of there. There's more chaos and also disorder. Right now, because there is a whole bunch of just female students in this classroom is pretty calm. But at the same time, if I took some immature young lads who are your same age because their maturity is not the same as yours, how do I know that? because I have a son and I have a daughter, and my daughter, man, I didn't have to worry about her. My son, when he was younger, I had to worry about him jumping off the couch and thinking he's Superman, and then the next thing I had to take him to an emergency room. I would never do something like that. If I brought a whole bunch of young men in this classroom, then I would be like, I can't teach here. There's too much chaos. They're acting immature in this case. So if we add more things to the pot, there's more chaos and more disorder that we're gonna have here. Even I can see here, solid, you're highly organized. Liquid, you're pretty organized. You're still slipping and sliding past here. But when I put this in there, oh yeah, that's even more chaos and disorder here. Easy enough. Next one. Wait, right here. If I look at it, I got this reaction. And basically what you're looking at is you're looking at the decomposition reaction for ammonia. So NH3 going to N2 plus H2. You have a 3 right here and a 2 right here. So that's what we're looking at. Can't we agree that because all of these are gases sitting right here, that the one that's going to end up having more disorder is really simply who has more moles of gas? You got 2. Okay, I can grab you 2. I got one in his hand right here. Over here, I got 4. I'll grab you. Oh man, chaos is flying all about. There's more chaos. One of the things that you're gonna have to do, and I know you'll be like, Mr. Carlson, this would be so hard when you make me do this tomorrow in class, is you're literally gonna be given reactions that might look just like this, where everybody's a gas. And you'll go in and you'll have this count. You got 2 moles of gas, you got 4 moles of gas. So clearly when this reaction takes place, the entropy is gonna end up growing in this case. Just like if I gave you something like this right here. Ooh, this is a good one. Ooh. This one is a tricky one. Because if you look at it, but actually it's still not bad. Is this leading to more chaos and disorder or less? Less.
Yeah.
Because I got 2 solids on this side, 2 solids, we have a solid, they're highly organized. But on this side, I got this gas that's all flying about, but all of a sudden, it's all organized now in something like this right here. We're always gonna just look at the gases. That's what we're gonna be focusing on in this case. Last thing we have here is temperature. Right now, if we were molecules are moving like this speed right here, so we're at a temperature, we'd be like, hey, going, have a little bit of chaos. If I told everybody to start running, hey, run! Oh, hit the wall, bounce off the gas bar, hit the wall. What's gonna happen to the chaos and disorder as the temperature increases? It increases. That's it. That's all I want to talk about for today. We're done.